Look at a weak acid strong base titration in terms of what's going on at a molecular level as a guide and overview to the calculations. And this one will primarily look at the titration at and after the equivalence point. Now, first of all, just a quick recap. We're titrating a weak acid with a strong base. And we're only going to show, in general, the predominant species in the solution. So when we start out, the predominant species, the high concentration species, is HA. And as just a recap before the equivalence point, so how we get to the equivalence point, when the strong base hydroxide is added to the weak acid HA, it undergoes a reaction to make A-, the conjugate base of HA, and H2O. So essentially HA molecules are being converted into A- ions, and as the titration continues, we have less and less and less HA, more and more and more A-. In the region around here, we have significant amounts of HA and A-, so we have a buffer. And as we keep going, we get less and less HA, more and more A-, and eventually we have so little HA compared to the amount of A- that we really don't have a buffer anymore, but we still have an acidic solution because we still have some HA. And then at some point we've added enough OH- to completely react with the HA, and we are now no longer before the equivalence point, we're now at the equivalence point. And the reaction we were using is no longer relevant because the HA has all been used up. So we now are going to take a look at what's in our solution at this point, at the equivalence point, which again is where the number of moles of added OH- is equal to the number of moles of HA we started with, and therefore is the amount needed to neutralize it. Well, it doesn't actually neutralize it, because if we have a solution where the predominant species is the weak base A-, then that solution actually is going to be a little bit basic. And it's basic because A- undergoes a reaction with water to a small extent to make HA and OH- ions. So the concentration of OH- ions is a little higher than in a neutral solution. The solution will be basic. It'll have a pH above 8. And we've done this before. We know how to handle base equilibrium as well as acid equilibrium. We do an ice table and we track the changes. A quick note, the concentration of A- here will need to be determined from the moles of A- that's been produced by the titration. And when we titrate, we're increasing the solution volume, so we'll have to take that into account when determining the concentration. But we can figure out our initial or starting concentration of A- if we assumed that the A- hadn't undergone this reaction. But it does a little bit, and we then, at equilibrium, know the concentrations in terms of this change X, which corresponds to the OH- concentration at equilibrium. We can set up our equilibrium constant expression for a base dissociation. We've seen this before, and remember that K sub B is very small. We can determine it from the K sub A value for the weak acid. And since K sub B is very small, X is going to be very small. And when we do our calculations, that'll allow us to do an approximation typically. And we will find the X value will be the OH- concentration at equilibrium. So then to get pH, we'll have to typically first calculate pOH and then use that to find pH. And again, the solution at this point will be somewhat basic. Okay, now what happens if we keep going at the equivalence point and we add more hydroxide? Well, there's nothing for it to react with, so we simply build up hydroxide in solution. We're now after the equivalence point, but we still have the equilibrium where A- is in equilibrium with H2O, a little bit of OH- is produced, but we actually have some OH- that just was added to the solution by the titration past the equivalence point. So for this calculation, it's the same type of thing as at the equivalence point, but we don't have a 0 initial concentration for OH minus. We have some unreacted OH minus that was just added. So we'll know the moles of added OH minus past the equivalence point. We'll determine the concentration of OH minus due to just that OH minus. And then we'll do the usual plus X and minus X thing in the equilibrium or in the ice chart. Do the equilibrium constant for the base dissociation, same idea as we did at the equivalence point, but our initial concentration of hydroxide once again is not 0. Remember again, Kb is very small, means X is very small, and when you do the math on this, if you're a little significant part way past the equivalence point, and you don't have to be too much past it, what you'll find is you do the math and solve, and essentially the concentration of OH minus that was due to the added OH minus past the equivalence point is going to be significantly larger than the X here that we would be solving for. And so basically, no pun intended, that ends up dominating the pH. And so we calculate POH from this equation, but we can use this approximation. And from POH, of course, we can get pH at any point after the equivalence point.